Hello, today my talk is on nanoscale control of the metal-to-insulator transition in freestanding lithium-aluminate strontium titanate membranes. So correlated electron systems has been revealed to have many interesting properties, such as superconductivity and ferromagnetism. Nanoelectronics help us to design quantum devices, leading us to investigate quantum simulation, quantum transport, and quantum sensing. Oxide heterostructures provide us with the opportunities to study these properties on nanoelectric devices. In our group, we study lithium aluminate strontium titanate heterostructure. By placing just under 4 unit cells of lithium aluminate on strontium titanate, we can control the metal to insulator transition locally at the interface with conductive atomic force microscope lithography. When we sketch with positive voltage on the tip, it can leave protons on the surface which attracts electrons to the interface, thus make a certain area conducting. The nanowire we write can be as thin as 2 nanometer. When we sketch with negative voltage on the tip, we can erase the written area, thus creating barriers in our device. Since we first report the nanoscale control of metal-to-insulator transition on this system in 2007, we put a lot of effort into this heterostructure. We developed a bunch of different devices. We studied the writing and erasing mechanism, and we investigated the strong electron-electron interaction at the 2D electron gas of the LaLO3 interface. Since then, we have already given 130 March meeting talks on this topic, and among all the talks, among all the devices we make, these two are really typical ones. So on the left is a single electron transistor, and on the right is an electron waveguide. Both of these two devices show strong electron-electron correlation at low temperature. So we keep thinking that what if we can integrate all these interesting devices with other materials, such as flexible materials, which may enable us to make flexible nanoelectronics, or ferromagnet or superconductor, which may lead us to investigate the proximity effect. And furthermore, we can integrate LaSTO with silicon qubits or silicon quantum dot arrays. If we can use the nanowires we pattern on at LaSTO interface as plunge or barrier gates for the silicon quantum dot array, it would be really interesting. However, directly growing perovskite on other materials such as silicon is proven to be really hard because of mechanical and chemical mismatch. So epitaxial sacrificial layer is another approach for producing the integrated perovskite and other materials. So here, as is shown here, Huang's group already use the strontium aluminate on the sacrificial layer to transfer strontium titanate onto silicon. They can achieve the transfer of SrTiO membrane as thin as 2 nanometer, and the chemical and structural properties of the SrTiO is well preserved during the transfer. Here we use a similar method to transfer LaO-SrTiO heterostructure. First, we deposit 20 nanometer of strontium ruthenate sacrificial layer on SrTiO substrate. Then we deposit 200 nanometer SrTiO and 10 UC LaO with PLD growth. And then we etch the strontium ruthenate away by sodium peroxide to release the LaO-SrTiO freestanding membrane. And then we transfer this membrane onto a different substrate with PDMS support. In this case, we transferred LaO-SrTiO to a sapphire. And this is how this membrane looks like under optical microscope. You can see that we can achieve millimeter size freestanding LaSTO transfer. And this XRD image shows that our LaSTO membrane is single crystalline, and this terrace on the LAO surface also indicates that the structural property of our LaSTO membrane is well preserved. And then we located the membrane and we etched to the STO layer to deposit interface electrodes, and then we deposit another layer of electrodes to serve as bonding pads outside the membrane region. And this is how a typical canvas look like under the AFM scan. And then we did a writing test with conductive atomic force microscope lithography on our LaSTO membrane. Here, when we write with 4 volt on the tip, you can see a conductance jump which is around 500 nanosiemens. This means that we can control the nanoscale metal-to-insulator transition on this membrane. And then we did repeated writing and erasing tests to investigate the writing voltage threshold for this membrane. As you can see here, when you write with 1 volt or 2 volt on the tip, the conductance barely changes. And then you can see when you write with 3 volt, you have a 15 nanosiemens conductance jump, and then the conductance jump increases monotonically with your writing voltage. So the writing voltage threshold for this sample is around 3 volt. And then we also want to investigate the low temperature behavior of the nanowires we write. So we make a device with robust lids which can be transferred into the fridge. First, we make this whole area conductive, and then we erase in the middle. After the conductance goes down to 0, we write a wire in between, and you can see this time the conductance, the 4-terminal conductance is around 4 microsiemens, and it decays much slower. This is the conductance versus temperature graph. You can see in the 2-terminal conductance, there's a turn up at around 300 millikelvin, which we attribute to superconducting feature. This is how the IV curves look like at low temperature. You can see here's a slight upturn in the 2-terminal IV curve, and from the differential resistance you can see also that the differential resistance around 0 current is lower than other area, and we think this is due to the superconducting behavior. In the 4-terminal wire, the superconducting behavior is not that obvious, but you can still see the lower differential resistance around 0 current. We also did a sweep in magnetic fields while measuring IV. You can see at large field, which is this red curve, the superconducting feature of this IV curve is suppressed, and you can see in this differential resistance versus B, there's a dip when the field is 0, which indicates the superconducting behavior is suppressed at around 1 Tesla, and we attribute the decrease of resistance at larger field to the localization effect of our device. So in conclusion, with the help of strontium ruthenate as a sacrificial layer, we can achieve the LaSTO heterostructure transfer onto a sapphire substrate, and the structural and electrical property of our LaSTO membrane is well preserved, since we can control the nanoscale metal-to-insulator transition on the canvas we patterned. We also observe some superconducting feature of our nanowire down to low temperature. So for the future, first we can optimize the membrane growth condition to achieve slow decay rate, and thus enable us to make more complicated devices on our sample. And then we can consider integrating with silicon electronics to see if we can gate our membrane device using the gold on silicon. We can also integrate our membrane with various kinds of 2D materials such as graphene. We can also integrate with flexible material, magnetic or superconducting materials. Thank you.